Lecture 28, Asynchronous I/O with AIO. All right, previously we had talked about if you just open a file and you say, I want this to be non-blocking, it doesn't quite do what we want because when you invoke it like this, you end up with effectively no real difference and the wrong outcomes because the file has data available. Whereas we saw that actually this is better suited to sockets because with sockets we know that there might not be data available if nobody has, say, sent us anything right now or there's no place to write any data. That would be a good indication that we can't use that socket right now and we would get blocked, and thus accessing it in a non-blocking fashion is sensible. There is, however, a way to accomplish what we want using the standard compliant asynchronous I/O interface, which we'll just call AIO from here on out because, well, it's shorter. So what we want to do follows this general approach that we create a control block. The control block is a struct AIO CB. CB for control block, that specifies what you want to happen. Then you enqueue it, that is, you tell the operating system that you want this to happen, do this thing, please. And when you are handing it over to the operating system, you have the option to specify that you would like a callback to occur if you wish. Callbacks, we know, are familiar to us now from curl, which we've seen on more than one occasion, so that shouldn't be so shocking to us, but we can do the same thing with an AIO control block. It's your choice. You don't have to. You can check periodically instead if the AIO operation is complete, if you would rather ask as opposed to have a callback notification, but both options are open to you. Okay, so let's take a look at the AIO control block structure itself, struct AIO CB. It has the following stuff in it. It has a file descriptor. All the names are prefixed with AIO, so I'll spare you from saying that part aloud. But it has a file des, a file descriptor. So what file do we want to perform the operation on? So is it we're going to read or write or something like that from a file? Well, you have to say what file is involved. So that's what we do. We have an offset. And the offset is how far into the file we start the operation. And the offset does nothing if the file is open in append mode. Remember, in append mode, you're always writing at the end of the file, so the offset is kind of meaningless. You're always just tacking things on, and that's really all that is relevant there. So that's what we would do with append, but otherwise use offset. It's also kind of noteworthy that when you do a read or write, the pointer to where you are in the file advances as per usual. So if you start at the beginning of the file and you do a read of 1,000 bytes, it reads 1,000 bytes and it updates the pointer so that if you say, okay, I'd like to read 1,000 bytes again, it reads you the next 1,000 bytes. And that works as expected, but AIO has its own pointers into the file. So if you have the file open for your process and you do a blocking read, so the regular read, the one that we are familiar with, that advances the read pointer, but not the one for AIO. AIO has its own pointer, and similarly, if you do an AIO write, it doesn't move the write pointer from the blocking one, so you have to be careful about this. You can't mix and match and expect you will get the normal behavior that you would get when you do standard reads and writes or just the asynchronous ones. So you do have to pay a little bit of attention to that. Okay, then we have a buffer. A buffer is, well, exactly what it looks like. It is the source for a write. This is the data that we are going to write out to the file, or the destination for a read. This is where the data read from the file should end up. And those cover the mandatory fields if we include also the number of bytes to transfer. So how much data are we writing versus how much data are we reading, depending on what our operation is. And those are the only ones that are mandatory. So we could skip the remaining fields, the priority, the sig event, and the opcode. We'll talk about each of those, of course, just to make it clear. And if you just specify those first four parameters and you enqueued the request, the operating system would know how to carry out what you asked for. It would say, yep, we could just skip right to that example if we wanted to, but I would rather tell you about all of the fields in here. Now, request priority is you can give a hint to the operating system as to how you think things should be scheduled. If you think this operation is more or less important than another one, you can indicate that by using the priority. Otherwise, just leave it at 0. I would recommend using memset on the AIO control block whenever you create it, and it just blanks out all the fields that you don't need / don't use, and that will suffice. So the priority is a suggestion. The operating system could ignore it. We'll just say leave it as 0 for our purposes. And then we have an event. And an event is complicated because it's its own structure, and it's called a SIG event structure. And we're going to have to open that up and sort of take a look inside of it and see what it does. There's also an opcode, which we are going to come back to as well. This is used for sort of mass management of asynchronous I/O control blocks. We will revisit that a little bit later on in the topic, but for now, just you don't have to use it for the standard mechanism, and so we can ignore it. But let's open up the event. Okay, so the event in AIO consists of the following things. It has an int SIG-EV notify, an int SIG-EV signal number. It has a signal value. It has a set of attributes a function and a set of attributes. Okay. This is probably the most complicated structure that we have ever looked at, and it is... Well, I'll put it like this. It's not how I would design it, because I think by trying to save a little space and pack some things together, it made it much harder to read and harder to understand if you're not really an expert in how this works in C. So, I mean, let's talk about it. So SIG-EV notify is an integer, but it's going to be one of the following constants: none, signal, thread. None means when the asynchronous I/O is complete, do nothing. Right? That's straightforward. It is the default, incidentally, if you don't put anything. If you just leave this as all zeros, then don't do anything when the request completes is what happens. Okay. If you choose SIG-EV signal, it means, well, specify a signal. You give a signal number, and it's generated when the request is finished. And SIG-EV thread is used to actually start a new thread. Okay, we'll come back to that. Let's focus on the signal start for now. So if you choose the signal approach, then you specify in the second part of this structure the signal number. So you want to send signal number 1, hang up, or something. You have a signal handler that's registered for it, and you say when the AIO is done, send me this signal, and then the signal handler will activate. So that'll work pretty well. The third argument is problematic, I think. It is difficult because it is a union. What is a union? In the context of C, not as an organization of workers. A union is kind of like a struct. It's sort of the cousin of the struct. A union is defined as being, it's one of these following things. So it is either an int or a void star pointer. And this is, well, there's a reason why I didn't talk about this in the first lecture when we talked about structures and we talked about how they work and all of that, because unions are rare and occasionally confusing. So I don't like it, but it's what's in the specs, so now we have to deal with it. We have to learn it, but hopefully at the time when you are encountering this, you've got at least some amount of C programming under your belt, so this doesn't seem like completely insane. Okay, so what about a union? So a structure is comprised of all of the following things, right? So if I have a struct point and it has three doubles in it, then x, y, and z, that structure has all three of those things, and the size is the sum of those elements. So the size of the double for x plus the size of the double for y and the size of the double for z produces 3 times size of double. That's the size of your structure. If you added an integer to that, well, okay, then there would be 4 elements in there, and the size would be 3 doubles and an int. And if integer is 4 bytes and doubles are 8, then 3 times 8 equals 24 plus 4 equals 28 for a total of 28 bytes for that structure. If you have a union, and union is defined here like this union sigval, its size is the maximum of the individual components. So it can only be one of those things at a time. It will be either an integer or a void pointer. Can't be both at the same time. Both these things don't have independent values, and the maximum size, again, if an integer is 4 bytes and a pointer is 8, then the union will be of size 8 bytes. Okay, so what's the purpose of a union? The idea being that you would use the SIGEV value you could either assign the integer or assign the pointer. You use the name of the property of the union. So when we want to assign SIGEV value .si val int, we do so, and it's responsible for figuring out the compiler is responsible for figuring out how to assign this and process it properly. The idea behind a union is that when we have a field that would be used only sometimes, we can share it with another field that would be only used at mutually exclusive times. You can save a bit of space. You can potentially reduce duplication of names if you have something that could take more than one type. So yeah, union is one of those like arcane space-saving, time-saving, name-saving features that I really don't recommend because I think it trades off too much readability for cleverness. In any case, I hope as we move through the example, it'll be a bit clearer. You just have to remember when we talk about SIGEV value that because it's defined as a union of int and void star, it can be one of those things, but only one at a time, and it can switch between them at any time. Okay, the union thing aside, the next argument next field in the SIG event structure is a function pointer, and it is a function pointer for a SIGEV notify function, which has return type void and one argument of type union sigval. All right, and finally, then there is a pointer to pthread attribute structure, which is going to be the attributes for the thread that gets created as a result of the event. So if we chose SIGEV thread, then the fields that are relevant are, of course, the notify type, where we said we want it to be a thread. We will use the union sigval SIGEV value to be the argument that's provided to the thread. We will specify the notify function. This is the function that I want to run, and we can use the attributes. If we're not going to do that, if we're going to use the signal version instead, then obviously we need SIGEV notify to be SIGEV signal, and we'll specify the signal number that we want to run. The SIGEV value can be used in your signal handler if you use a somewhat more clever mechanism for handling signals that we didn't really go into about SIG action as opposed to just the signal system call, but we're not really going to worry about that. What we will say is that if we're going to use the signal in the simple approach, you just use the signal number and the rest as the notify argument. It doesn't matter. If you're going to use the thread, then you need the remaining 3 fields, the SIGEV value, the function, and the attributes, although attributes can be null, and you can ignore the signal number. But yeah, the function definition for the thread is not exactly the same as we're used to. But it is straightforward enough. Now, we can send a signal when the AIO is complete, but I don't think we're going to do that very much. I don't think there are any examples that cover it, because we'll use the thread approach. The thread approach is quite flexible, and it's a good way of doing this. You can trigger a specific action. A signal is fairly limited because you start the signal and it's picked up by your signal handler, and your signal handler takes some action, but as you remember from our discussion about signal handling, there are some pretty significant restrictions on what you're allowed to do within a signal handler, because whatever you're doing has to be async, safe, and can't interfere with anything. So that is reasonably limiting. As a result of that, it's a little bit better in a lot of scenarios to just create a thread. And so we will choose that option. It's important to remember actually that the function that we specified is executed in a new thread, and it is a detached thread. Okay, so let's imagine then, after there's a fair amount of work, but after all of the work to prepare our AIO callback request, we can then enqueue it, and there are two separate functions for enqueuing, one for enqueuing a read and one for enqueuing a write, and they are called imaginatively AIO read and AIO write, and they are, again, straightforward because they only ask you to specify a pointer to the AIO control block that you want to enqueue. One thing that is important to note is that you may not change the AIO control block or the buffer, the source or the destination for the data, while the AIO operation is in progress. Now, perhaps you're thinking, why is this a concern? Well, one thing that I have seen, and this was observed during a previous in-class exercise, is that if you write a for loop and you stack allocate your AIO control block, so you say, okay, for in I equals 0, I less than number of files, I++, and then you just stack allocate your AIO control block, and you populate all the fields, and then you call AIO read with an address of this AIO control block. On the next iteration of the loop, you end up overwriting that AIO control block, and so things go wrong because we've changed the AIO control block while the operation is in progress. And you shouldn't do that because the operating system will get to it when it gets to it, and you will get inconsistent results if you do so, because you're sort of changing things out from under it, which is unlikely to go well. All right, are we there yet? I mean, we could, of course, set up a signal or a thread or something that tells us when we're done, but it's not the only way. We can also check whether or not the operation is finished. And there are two options, AIO error and AIO return functions. So AIO error, I think, really should be called AIO status, because it also tells you if everything is fine, not just, in case of error, this function runs. So yeah, it tells you the status of the operation. If you call AIO error with a pointer to a particular structure and it returns 0, that indicates that the operation is complete. If the operation is still pending, that is, it hasn't started yet, it's still waiting to run, hasn't been started, or if it's actually executing right now, both of those show up as E in progress, so that tells you that the operation is not done yet. Now, if the operation completed successfully, then you can use AIO return, and that gets you a return value from the read or the write operation. So if you were doing a read, for example, it tells you the number of bytes that you read, if you care about that, but that's why it returns a size type. It returns, oh, we asked for a read this many bytes, well, here you go. This is how many were actually successfully read, if you care. If you don't, you still need to use AIO return because AIO return deallocates some structures. In the same way that a thread could have some stuff sort of still hanging around waiting to be collected by a pthread join, or a child process is a zombie until a parent collects its results, the AIO is the same way. The results information can't be deallocated, and the other associated information can't be deallocated until someone has come by to collect it. Even if your intention is to do nothing with the results, you should still use AIO return because it cleans up the AIO control block stuff because, well, it's no longer needed. Now, someone came and collected the result, which was all that was being waited for. Okay, so let's consider an example, and I'm going to call this example read while you eat. What do I mean by that? Well, suppose that we have been asked to design a program that processes a group of files. You could, of course, create a new thread for each file, but let's assume that we don't want to do that, and we want to do it using the AIO approach. And we could use AIO to partially parallelize this. So we'll say in the first version that our goal is just to partially parallelize it. We want to start the read for file n+1 and then process file n in the meantime. Obviously, this doesn't work for the first file because there is no file preceding it, so you have to do a blocking read that takes place first. I've assumed for the sake of simplicity, in this case, the maximum file for any size you'll read is max size, so you just try to read that many bytes. If that doesn't give it away, this is because this was at one time an exam question in a different course, and based on that, this was a simplifying assumption that said, well, to save you from using the IO control function to ask about, or the stat function to ask about how big a file is, which is presumably what you would do in a real example, but on an exam question, the goal is just to demonstrate, can you do the AIO stuff and not can you figure out the size of the file with stat correctly? So sometimes a little shortcut is provided that says, just don't. We'll do this instead. Okay, so what we're going to do is have two buffers. We'll have one for the file that's being processed and one where the next read is taking place. So we have a first buffer, and we read the first file into that buffer. Once we've done that, we can start the read for file number 2 into the second buffer, and then we can start processing on file 1 using buffer 1. Read is potentially slow, as we know, and requires the disk, especially if it's going to like a hard drive or something. So it could take a little while. And that being the case, don't wait for it. Don't bother. We could do something useful in the meantime and save time, but again, without using threads. So we have two buffers to make this work. A list of files to read will be provided as arguments on the command line to the program, again, another thing that gives away that this was an exam question is to make the code more compact, assume errors don't occur, and we don't have to check for them. Also, for simplicity, what we'll do is check completion and use sleep if we need to wait. We could improve on that later, but for now, that is our approach for what happens if, say, we're done processing before the read is finished. Okay, so we'll assume that there is a function process which takes a buffer. What it does is not important, so its implementation is not shown. And we'll then do the rest of the setup. Also not shown are the rest of the headers, but it is necessary to include the header AIO.h and to compile with the -LRT option. No, not light rail transit, but I understand why you might have guessed that. Okay, so main allocates two buffers, each of some fixed size, max size times size of char, and we will open the first file, open it read-only. We will memset our first buffer, and we will read from that file into that buffer and then close the file descriptor. So that's the first one. It is the first like blocking read sort of thing, and we're quite familiar with that. Okay, and now let's actually do the asynchronous I/O part here. All right, so starting at I equals 2, I less than argc, so the count of arguments, I++, we'll open the next file, whatever was provided on the command line, and we'll open it read-only. We will declare our struct AIO control block. We will memset it to all these zeros, and then we will populate all of the fields. And this is the minimal version, so we don't have to fill in every single one, just a few. And that being the case, there's not quite so much to it. Set the number of bytes we want to read to the max size. Set the file descriptor to be the next one. Offset is 0. We'll memset the destination buffer here. So buffer 2 is memset to 0. And then we'll assign that buffer. And then we'll enqueue the read and go on to process. And so we're processing buffer 1. Now, it could happen that processing is finished before the read or vice versa, and that's what the little while loop there is for. That we'll do while AIO error is still in progress. We will sleep and wait a little bit longer. Once that's done, we'll use AIO return. We're not interested in reading the results, but you could, and it just frees some internal structures, and we'll close the next file descriptor. And then the last 3 lines just swap the identities of the buffers. We just update our pointers. So buffer 1 was the one we just finished processing, and we're going to say now swap its name with that of buffer 2, and that's what the swap is about. And so on the next iteration of the loop, we go around and we open it, and what was previously called buffer 2 is now called buffer 1, so that's going to get processed, and the original buffer from the first file is going to get memset and get the data written into it from the file. So that's the basic premise of this example. You'll notice I said something about how you can't mess with the AIO control block, and I gave an example involving, well, if you use a stack allocated one and you do an AIO read with address of, you could get in trouble, and you think, like, why I'm doing that thing here. Yes, but I'm also making sure that I'm only ever working on the AIO control block when it's not running. So we do the AIO read, we enqueue it, and then we don't touch it again until the next iteration of the loop, and the next iteration of the loop is after it is complete, because we pick that up by checking with AIO error. Again, I think it should be called AIO status, but that's not up to me. And only when we're sure that it's actually done, then we can go to the next iteration of the loop, and then we can change it because it's not in progress anymore, so no harm is done. Okay, and once we've finished with the loop, there's a little bit more. There's one more process of buffer that has to take place, because if we go back, on the last iteration of the loop, we will read the last file into the buffer, and we will process the second last file, and so when we exit from the loop, we will still have one as of yet unprocessed buffer, and therefore we need to explicitly do that here with process buffer 1 here at the end, and then we can deallocate our buffers, and we're done. Okay, that's a simple example for how to use the how to do the AIO control blocks, and how to use them and how to enqueue them, thus allowing us to partially parallelize some of our code. But as you might imagine, this is not optimal. Is sleep really the best way to deal with this? I mean, maybe we have something to do in the meantime, so we're always certain that the read will be finished before our execution. Could happen. Maybe not. But if not, why don't we get blocked? Isn't that better than having this check and sleep and all of that? And for that, there is a function, and it is AIO suspend. All right, AIO suspend takes 3 parameters, and it's really not too complicated as we can see. It takes an array of control blocks, and that's called the list here. So we have a pointer to that array. We have n-ent, the number of entries. This has been auto-corrected on the slide to say went instead of nent. Don't ask me why autocorrect thought that would be correct, but that's what we ended up with. And timeout is how long we're willing to wait. Time spec, you will remember, I think, previously from our discussion of asynchronous I/O with select and pselect, so we know how to make a time spec, and that's just how long you're willing to wait. This returns 0 if the AIO operation is finished, and -1 if the timeout is reached. Now, it does return when any one of the AIO requests in the list are finished. So it doesn't have to wait for all of them to be finished. We'll wait for at least one. If all of them are finished at the time when this function is invoked, then the function does not block. So we will just proceed immediately. So suspend can't do any harm. No. So let us proceed on to a second example, one that talks about how to use a callback. And this uses the function callback, and we're going to make it a little bit silly, but it should be sufficient as far as we're concerned. So, all right, we have to include a whole bunch of headers, including the AIO header and the file control one, string and arrow and all that for the example to be complete. But that's a lot of headers, and we'll define the maximum size here to be 512 bytes. And also shown is the definition of this is the thread is going to run this function. So that's what happens when we trigger a thread. It runs this function. Again, the signature for this is not exactly the same as for a pthread. For a pthread, of course, you will remember that we use void star return type and then a void star argument. Now it is a void return type and a union sigval argument. Now, so we're going to unpack the argument, and the argument is going to be well, it's going to be a pointer. Like with the pthread, we have to decide on our own, what does the convention mean, so what is the caller going to provide so that the recipient knows how to get it. And we're going to look inside that union, and we're going to choose to interpret it as a pointer, and to do that, we use the variable SIVal pointer. If we go back to the definition of how we actually do that, it is a ways back here, right? The sigval union here is either an int or a pointer, and we're saying we want to interpret it as a pointer, and we do so by using this name. That tells the compiler what we're looking for is we want to read the correct amount of bytes for actually treating it as a pointer. If we used the wrong name, we would try to read the wrong number of bytes because the compiler would say, well, you were looking for the int, and I know what the size of the int is, so that's how many bytes of a read is going to occur. And then we use these two different names. Maybe that illuminates a little bit why it's called two different names and a union isn't just a list of sizes. But okay, back to our example. Right, so at this point, the definition of the worker thread is fairly straightforward. It's just we cast the type here, so it's a char star. And then worker thread says it's here, and it prints to the console, and it says what the buffer contains. And then we can deallocate the buffer. That, of course, has to be paired with our main function, and the main function is also quite straightforward in this scenario. We will allocate a buffer, we will do an open of the file that we want to read, memset our buffer, declare our AIO control block, and memset it as well, keeping in mind it's full of fields we don't need, so it's important to memset them so we don't have garbage in there. And then we'll set our number of bytes to be the maximum size, our file descriptor, our offset is 0, our destination is the buffer, and then we will say our notify type is thread. The function that we want to run is called worker, and the argument, the SIGEV value dot SIVal pointer is buffer. Then we'll do the AIO read, and then we'll pthread exit with null. Now this will wait because we have the pending thread that is necessary. It is a detached thread, so the pthread exit will keep hanging on until that thread is finished. But the thread will run. It will read whatever content was in example.txt and then print it out to the console, and we're done. The important part about this, are these lines here about where we're trying to configure our callback. It is relatively straightforward. I mean, it is a bit of a pain that you have to know cb.aio sigevent.sigevent notify is this, but ultimately it's reasonably manageable. What about cancellation? So there exists the ability, of course, to cancel a request. If you decide that you no longer need it, then you can do so, and you will then specify cancel FD and an AIO control block. Why the file descriptor? So cancel comes in sort of two variants. One is I want to cancel a specific AIO control block, so just this one operation is no longer needed. If that's the case, you specify on this file, cancel this AIO control block. And if you only have the AIO control block, don't despair, because it itself contains a reference to the file descriptor, so it's not like we'll forget. So that part is no big deal. However, the real reason why file descriptor is there, because you could say, well, can't it work out what you wanted automatically? Yes, it can. But the real reason why file descriptor is there is this grants you the ability to cancel all AIO operations on that file. If you give null as the AIO control block argument, then it tries to cancel all of the AIO operations related to that specific file. So, good. That's what we'd like. Did you notice something? Yeah, you noticed that I said tries to cancel, didn't I? In the words of Yoda, do or do not, there is no try. Thing is, this function returns one of 4 values, and they all mean different things. AIO canceled means that you requested to cancel some operations, and all of the ones that you requested to be canceled were in fact canceled. So if you only asked for one, that one was successfully canceled. If you asked for 3 of them, those 3 were successfully canceled, and that is total and complete success in what you asked for. AIO not canceled. Well, that means at least one operation could not be canceled. So maybe none of them were canceled, maybe one was canceled and the rest were not. You don't get very specific information about which ones were canceled and which ones were not, and you might find that to be kind of frustrating. I think it's a little unclear, but that's the potential outcome that you get, which is unfortunate, but it is a limitation. -1. Something went wrong during canceling, and you can find out exactly what by looking at the error number variable, as is typical. And AIO all done. We were too late with our cancellation. All done means all the operations that we wanted to cancel were finished before we could get to actually canceling them. So that can happen as well, because we might have waited a long time, but hey, while we were waiting, those operations did finish, and accordingly, there's no longer really anything to cancel. So there's nothing to do, and we'll be told all done. So we'll follow that with a super silly example in which we're going to just cancel immediately an AIO operation that we have completed. It doesn't really correspond to any meaningful example. You wouldn't do this in real life, but if you just wanted to see an example of how do you put the cancellation call in, here's what happens. We set up our AIO control block as per usual. We memset it. We set bytes, file descriptor, offset, buffer, all of that. And after we've done the AIO read, we will then do the AIO cancel. There is a sleep in there just to spend some time just to make it a little bit more pleasant so that there is actually something that happens. And that's it. We're done. Close the file descriptor and return 0. This is over. One last thing. You can right my wrongs. You can be better than I was. You can save this city. The list. The list. In the AIO control block, there was the last parameter. It was the opcode. And I said, well, the opcode thing is something that we will return to. Well, we haven't yet. And there's no time like the present. So the LIO opcode, the list IO opcode. What does it do? Well, the thing is that instead of submitting these operations one by one, we could submit a group of them all in a single operation. What do I mean by that? So consider if we had 15 AIO reads that we wanted to do, we could create an array of 15 AIO control blocks, and then for int I equals 0, I less than 15, I plus plus, AIO read, and then array at index I. That would work. That would be fine. That might not be the most efficient thing, though. Right? Every time we call AIO read, that is effectively a system call, and we are going to have to wait for that to be finished. It does have the advantage that we start the first one as soon as possible. If it takes some actual work to assemble and prepare the AIO control blocks, then you might prefer to do that. However, you might also say, couldn't we just start all of them or enqueue all of them really at once? And that's what the list IO operation is for. And the list IO operation takes the following arguments. It takes the mode, the list of AIO control blocks, so a pointer to the array that corresponds to them, and the number of entries in the list. This time autocorrect didn't bite me on that, so that part is spelled correctly, so hooray. One small victory. And sig EV is an event that fires when all are complete. Okay. We'll go through each of these in at least a little bit of detail. The first argument, mode, is you choose between either wait or no wait. Wait is blocking, so this function does not return until all operations are complete. And if that is the case, then the last argument, the signal event, is simply ignored. It serves no purpose because our intention is to wait. So we have decided we're going to enqueue all of these asynchronous operations, and we're just going to hang around, do nothing, get blocked until that is the case. If you choose no wait, then it is, of course, non-blocking, and as soon as the requests have been enqueued, you can just go on. You don't have to wait around, and that seems, to me anyway, much more likely what you would probably want to do. Then we have our list, the array of AIO control blocks, and that's not surprising. We have to have our array to actually do something, otherwise it doesn't work as expected. What is it? It's no different when we actually implement those, we provide them as before. The only difference is that we have to use the last argument. We have to specify the opcode, because the list here could contain read or write operations or both, and then we have to specify on each individual operation whether we want it to be a read or write or actually do nothing, as we'll see on the next slide. Number of entries in the list is straightforward, and the sig event here fires when whatever our whenever all of these are complete. And sig event, again, is like our previous definition for a particular AIO control block, but this happens only when all of them are complete. So you could have your array, and it has AIO control blocks, and each of those can have their individual callbacks, and those all still take place. That part is not affected if you use the this final one. However, it is an extra one that is used when absolutely everything is complete. It's an extra that's available when you need it, but you don't have to. You could provide null for this parameter if you are so inclined. Now, if you are going to submit it using the list operation, it is important to specify, as I said, what operation you want to occur. And your three options are read, write, and no op. And no op means do nothing. And so why would that ever make sense? Well, sometimes you will have a list that's pre-prepared, and you will decide sort of at the last minute that you don't need this operation to proceed, or you have a list of these are the 10 AIO operations that could occur, but will only activate the ones that are relevant right now, in which case, again, you just specify these are the ones that I want, and the rest can be no op by default, and that is sufficient. So that's what this is for. So what we can do is go back and revisit a couple of more examples of use of AIO before we wrap up this topic. Okay, there's one more thing that I have to point out, and it is the implementation in Linux of AIO actually uses threads to do blocking reads. Ouch. Work continues on this subject. There have been a couple of attempts to get merges approved into the kernel that address AIO to make it work a little bit better. The actual implementation of how AIO works isn't really your concern as a caller, as a user. People have been working hard on an actual implementation of it to actually get correct behavior. But this is a standards compliant mechanism for using AIO, so it would be different on different systems. In Linux, it's implemented like this, but on FreeBSD or something, it could be implemented completely differently. I don't know off the cuff if they do the same thing, but they might not. So the poor implementation, as it is, doesn't actually affect your program too badly. It's just one of those things where it's like, wow, that's unfortunate. That it seems like it should be better than creating threads and having them do blocking reads, but that's actually the shortcut for how it was all implemented. Whoops. So if you want to create a very large number of asynchronous I/O requests, then actually what you really probably want to do is use a library that's better suited to this, and that brings us back to libevent. Libevent I mentioned previously when we talked about the linear characteristics of select and poll, and I said, well, we could use libevent for high performance situation, and the same applies. You could use libevent for files as well. So that's what we're going to do next in what is really the last big topic of this course. So I'll see you at that video.